One thing astrophysicists know but they don't like to talk about is supermassive black holes disprove the Big Bang Theory. And supermassive black holes have been in the news because they're pretty certain they've discovered one at the center of the Milky Way, and it's believed that they're in the center of all the spiral galaxies, which is a large percentage of the galaxies throughout the universe. So there's billions and billions and billions of supermassive black holes. And the normal supermassive black holes start at about 100,000 or a tenth of a million up to 1 million solar masses in size. So you can think of 1 million stars the size of our sun being combined into a single black hole, that somehow all that mass is combined. But then there's ultramassive black holes, which can be 1 billion solar masses or more. So up to 1,000 times bigger, or actually 50 times, 50 billion, 50,000 times bigger. So this is a huge amount of material that has to find its way into a black hole. And the reason why that's a problem is black holes have to start out small, because the largest star we've identified to date for certain is about 265 solar masses, and a more typical large star is more in the 100 to 150 solar masses. So you can start with 100, but you have to get to over 100,000. That means that you're looking at 1 billion or more stars, or the mass equivalent of 1 billion or more stars, being combined into a supermassive black hole. And that's difficult. If you look at our galaxy, the stars orbit the black hole. They have enough velocity they orbit. They're not falling in. The myth of the black hole that eats stars it's just simply not true. The stars orbit. Provided their initial velocity is high enough, they continue to orbit. There may be some that weren't orbiting very fast that get gobbled up initially, but eventually they just continue to orbit, and you don't get the rapid star growth. There are mechanisms for them to slow down and eventually fall in, but the black holes don't really grow that way. They actually tend to grow more from gas, it's thought. So you have to have a huge gas ball. And so this process is called accretion, where you slowly add more and more gas to the black hole. But this has its limits, because as the mass increases, the volume increases with the cube of the radius, but the surface area only increases to the square. So while maybe initially, as it gets more massive, it'll grow more rapidly, over time, you end up with a bit of a roadblock, because you have a small surface area and you have a lot of mass that is necessary in order to increase the mass of the black hole to these types of levels. So you end up with the matter density getting high, which that produces heat. And then when you get enough heat, you can actually produce light that we can measure. So we have this roadblock. And if you took just a linear extrapolation, some just basic estimates using normal gas models are that it would take the entire life of our universe just to make the 100,000 mass black holes. So 1 million mass black holes, assuming just a simple linear approximation, which obviously isn't true, but I'll use it to illustrate the point. 1 million would be 138 billion years. And then 1 billion would be 138 trillion years. And then 50 billion would be 6,900 trillion years. And that's the problem. Even if you come up with ways to accelerate this growth, hypothetically, you're still looking at a time frame in the trillions of years, which doesn't fit with the Big Bang model. And that's why the supermassive and ultramassive black hole problem disproves the Big Bang. It basically shows that a 13.8 billion year time frame is insufficient for these ultramassive black holes to exist. Now, astrophysicists do come up with modeling programs to try to overcome this difficulty because they're stuck on trying to make the Big Bang theory work, even though there's probably 50 reasons why at this point while it doesn't work. And one, they'll say, oh, there were initially bigger stars, that you could get ultramassive stars rather than the small ones are only 100 times bigger than our sun, that there might be some that are thousands of times bigger than our sun. And that gives you a little bit, or even more larger. And then they also will say that, oh, the accretion rate's different and somehow the matter moves more quickly and gets absorbed more quickly. And so they have theories about that. But, you know, we understand how gas molecules interact quite well. That, in fact, I mean, gas theory developed well before quantum theory, and so by the middle of the 1800s, physicists had a pretty good handle on how gases interact and plasmas to a lesser extent. But so you can come up with new models, but are you talking about something physically real? And that's the problem with astrophysics in general, is they tend to write models to get the answer they want without necessarily proving that what they've written reflects physical reality. And the biggest problem underlying this, if you assume a gas model, because like I said, stars are orbiting, they're not being really sucked in. If you assume slower moving gas cloud, you have to have huge gas clouds that are very dense in order to have all that gas sucked into a black hole. And so right off the bat, you have to assume a much bigger gas cloud in order to get a supermassive black hole in a short time frame. Now, they do have to consider galactic collisions, and if you do have black holes collide, that's one way to grow them. But there's also theories that when galaxies collide and they have their supermassive black holes, that they don't join up very often. And sometimes you have an orphaned supermassive black hole that gets stuck in a galaxy, or perhaps gets ejected out into space by itself without a star covering. So galactic collisions aren't going to get you there. And they're too infrequent to grow the mass that rapidly anyway. And my favorite is that people don't talk about is actual internal mass production. That would be the way to get there the fastest, is if you're actually producing protons and electrons inside the black holes and inside stars. And because that would allow you to get production faster. But the Big Bang theorists don't want you to have steady state production. They want the laws of physics to change over time. The laws of physics have to be different at the beginning of their hypothetical Big Bang than they are now, in order for there not to be matter production now. Because if there's matter production now, then they really need to switch to a steady state model. And ultimately, I think we will show that we will be able to prove experimentally that we can produce matter under certain conditions. That's matter without antimatter, to be clear. And that once we do that, then it'll be obvious. Until we know how protons and electrons are produced without antimatter, then much of cosmological theory is guesswork. Once we know that, then we'll have a much firmer basis for understanding cosmology. Now, the problem with age is not just related to the ultramassive black holes and the supermassive black holes. We have things like the Methuselah star and other stars that appear to be older than the Big Bang timeline. And some of those, they've had their age estimates fudged downward through the years to fit the narrative. And that physicists will continue to do that are trying to rescue this failed model. And then we have our Milky Way galaxy. And many stars in the Milky Way galaxy bulge are thought to be up to 13.5 billion years old, which means that basically our galaxy is already as old as a galaxy can get within the 13.8 billion time frame, because it takes a couple 100 million years for the stars to start to form, and then it's going to take time for the galaxies to form. So the Milky Way galaxy is, under the Big Bang theory, as old as a galaxy can get. And that's a problem in that if in physics and in science in general, you shouldn't assume that you have a special position. You shouldn't assume that you're in the oldest galaxy or that you're in the center of the universe. You shouldn't make assumptions like that. Because once you do, you're in trouble, because that means every other galaxy is younger that is further away. Because if it's 10 billion light years away from us, that means we're seeing light from a galaxy from 10 billion years ago. And if that galaxy is just as mature as the Milky Way, then it's 25 billion years old, at least, for one that's 10 or 12 billion years away, billion light years away. And so that's a huge problem with the model. If you assume that galaxies out there are the same as the Milky Way, then they're much older than is allowed under the 13.8 billion light year model. And that's why, assuming that we live in the oldest galaxy, or one of the oldest galaxies, then you throw the whole Big Bang theory out the window. And that's not to mention the galactic clusters, because the galactic clusters are even more complex and take even more time to develop and could be 10 or 20 billion years older than the galaxies themselves when taken all together. So you could be looking at 35 or 45 billion years to take the time to develop the galactic clusters we see 12 billion light years away. And then there's walls and voids. And at the velocities that most of our galaxies are moving, these walls and voids and some other structures that are sometimes in the news are over 1 billion light years long. And in order to get a structure that long, it's going to take 1,000 billion years at a reasonable velocity. So you're looking at needing a trillion-year age of the universe to describe some of these structures. And of course, it could be much longer than that. It could be 1,000 trillion, or it could be infinite, perhaps. So there's a huge problem with cosmology in that, and the Big Bang theory in particular. And at the heart of it, and the worst time limit that we know so far, are these ultramassive and supermassive black holes, because they require the universe to be much, much older than what the Big Bang theorists claim it to be. Well, I hope you enjoyed this video and hope you learned a new perspective or got reminded of a perspective you've heard of but tried not to think about. And if you like this video, like it, share it with your physicist friends, subscribe for more of my physics videos, and also a published author. I have books for sale, and if you buy one of my books on quantum field theory and particle theory, you can learn a lot more about those aspects of physics and help me out in my research by buying a book. I will say I haven't written a book on cosmology because I'll do it as soon as I understand how protons and electrons are produced, because then I will know a lot more about cosmology, the cosmology of the universe. Well, thanks for watching.